Hello, everybody, and welcome to another week of Dome to Home. My name is Jeremy. I will be the navigator for you guys today, which means I'll be controlling everything that you guys are seeing live. And this is a very special Dome to Home because you may notice someone that we haven't seen before on this series. This is a series about water. We're going back a month because unfortunately we had to postpone this special episode. But today we're going to be doing some kind of comparative planetology, looking at Earth, and then doing some comparisons to Venus and Mars and how water, how it survives on the surface, how water interacts with the planet, how the planet changes over time. And I'll let Dave above me do most of the talking today because he is the expert. He is Dr. Dave Brain. He works at CU Boulder in the Astrophysical and Planetary Sciences department. He does a lot of work with Mars. He's kind of done it all. He does a lot of mission work. He does a lot of studying on of atmospheres and how the atmosphere of a planet escapes and how that kind of shapes a planet over time and how it changes. He also teaches, and I know I'm going to be probably missing a lot of the things that Dave does, but we are so welcome and we're so happy that he's here with us today. Dave, how you doing?
I'm doing great, Jeremy. Thanks for having me, and it's good to see you again. I've known you for a long time now.
I know it's still doing the virtual things. Unfortunately, we can't be here at Fiske Planetarium, which is what we're looking at here on the dome screen, right now. But we make do with what we can, right? And so we're glad to be able to continue these virtual shows as best as we can.
That's right. So let's dive in. Let's go for it. So on your screen right now, you're looking at Fiske Planetarium from above here in Boulder. And this is the place where, if we were all in person together, the place where this program would be taking place. And I want to use this as a starting point to tell you about where in the solar system we find evidence for water. One good piece of evidence that I'm noticing right now as Jeremy starts moving the view around is actually in Jeremy's background of his image. You can see the flatirons here in Boulder behind Jeremy. That's his background, and they are covered in snow. And every time I see this in Boulder, I think of powdered sugar, that someone took a giant bag of powdered sugar and sprinkled it over the flatirons. And I think it's beautiful, but it's also water that exists here on our planet. So in the open space software that Jeremy is operating, he can go anywhere on Earth and anywhere in the solar system. So we're going to show you several places in the solar system that have evidence for water. And we're going to also focus a bit on where that water might be liquid. So where are you taking us now, Jeremy?
I'm just going to go ahead and get kind of a top-down view, kind of see if we can get it up into the mountains. So open space uses, a lot of live satellite imagery and a lot of live data sets. And you might have noticed if you're in Boulder or somewhere in the Colorado area, it might not look like what the view we're showing you right now. So I'm just kind of going to fly us around over it, maybe look at some lakes, some other water features, and see if we can find maybe some snow-capped mountains.
Great. And if we can't find snow-capped mountains here in open space, that means that within the past week or two, when images of the Colorado mountains were taken and incorporated into this software, that means that there wasn't a lot of snow there at that time.
Exactly. Yeah, so it looks like maybe we're not, it has been a very spotty winter, as maybe some skiers could tell you. So maybe we hit a little dry spell when we're in the stuff that we're showing you right now. But you can see a lot of these kind of rivers and some of these channels. And we're going to take a look at some of these other features at a couple different locations here on our own Earth.
Okay, so yeah, let's leave Boulder. And if you're in Boulder today, you have more evidence for the fact that water is abundant here at Earth's surface because it's falling from the sky right now. And later today, it will probably turn into snow. But now let's go basically completely around the planet to a place near the Himalaya Mountains. And it's a place called 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐬, which is a mouthful, but it's a beautiful example of a river system here on Earth. And I want you to, once we get there and once we look at it, I want you to sort of remember what that looks like, because we're going to do some comparison here in a minute or two with some features on other planets. So as we leave the United States and go up, 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 and look at Earth as an entire planet, you also will see other water-related features that we could see from very far away on Earth.
Hopefully, as they start rendering out.
That's right. Well, you'll see things like oceans. There's a lot of water in liquid form, and all life needs water in liquid form. You may see polar caps as well. Antarctica is a landmass near the South Pole, and it is covered in snow and ice. And at the North Pole, there is no landmass, it's just an ocean, but the amount of ice cover shrinks and grows and shrinks and grows with the seasons.
So I just want to remind people too that when we're, looking at some of these different locations, you might kind of notice that it takes a little bit longer for some of these scenes to render out, and that is because they are live, or is close to live images of actual satellite data that we can get here. So this is all real imagery taken from space, and sometimes it takes a little bit of time to be able to really have a computer render all that stuff out. So here we are on the other side of our globe here.
Wonderful. So as Jeremy starts to zoom in, see if you can find evidence for liquid water yourself. Of course, I see a whole ocean there in the corner, the Indian Ocean.
Yeah, start to see some of the, similar maybe mountainous regions. These look a little bit more snowy than our own Rockies that we were just looking at. And I think what we want to focus on is starting at this, where this river kind of meets the ocean right here. And we're going to follow this all the way up from the ocean, all the way up into the Himalayas.
Great. So you could see where the water met the ocean, but you can see the river move back uphill, basically onto the land to higher and higher elevation up into the mountains. And as Jeremy takes us to lower and lower elevation, you can see that the river system is very complex. It's not a single river. Down near the ocean, at the very downhill part, it is a single wide, deep, fast-running river. But the higher you go, the more fine it becomes, the more detailed it becomes. It has small tributaries, places where water has flowed downhill just in very specific locations. And all those locations where water has flowed downhill come together to make a river that gets larger and larger and larger as you go downhill. And Jeremy can show us even an image of what that river looks like taken from an airplane or a drone instead of in the open space software. And you can see this really complex river channel where water has flowed for long periods of time over the surface, and it's in liquid form. And if you are on a planet and wondering if life can survive there, one of the first things you'd like to look for is whether water can exist as a liquid. So these are just a few examples of where you might find water on Earth. I'm sure you can think of many other examples yourself, places where water can hide on Earth. It can hide in the clouds, it can hide underground, even in underground rivers, or something called groundwater that seeps up. But there are many places on Earth where water can be liquid. However, let's leave Earth and go look at two other planets in our solar system that may or may not have liquid water. So I see a question in the chat from Denise, and she's asking how much of Earth is made up of water. And in terms of what percentage of Earth's surface is covered, it's 70% of Earth's surface, give or take. So that's more than half. Almost 3/4 of Earth's surface is covered by liquid water. And if we're talking about how much of Earth is water by mass, if you compare the whole, how much Earth weighs and what fraction of that weight is water, it's a much, 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 much smaller fraction. I actually don't know the answer, but I think it would be on the order of no more than a couple of percent and maybe less. So that water gets spread out over the surface over very large areas. Okay, so I think Jeremy's taken us now to Venus. Is that right, Jeremy?
That's right. Here we are. We just kind of zoomed across the solar system a little bit in using the power of open space, of course. And now we see Venus.
Okay, and let's look for water on Venus. Good job. We're done. There's no water on Venus, people. I'm very sorry to report.
Oh, there's got to
Venus
be
is
more than
hot.
that, though.
That's right. So there are interesting things to see on Venus, and those interesting things tell us that water doesn't exist on the surface of the planet today in liquid form. It's too hot. Venus is something like 700 degrees, and that's in part because it's closer to the sun than Earth, and in part because it has a really thick atmosphere of carbon dioxide, has very strong greenhouse warming that makes the surface incredibly hot. When we look at the surface, we don't see any evidence for old lakes or old rivers. Instead, we see a surface that's been covered in volcanic lava almost over the entire planet. There are very few things like impact craters and very few other features to see. And when we look at the atmosphere holds very little water also. Even though it's a big, thick atmosphere, there are no clouds of liquid water. The clouds are made of other things. So if Venus doesn't have a lot of water today, maybe it had some in the past, and we'll talk about that in a minute. So the image that you were looking at there for Venus is actually a radar image. It's not a visible image like we would make with a camera, with your cell phone camera or with our eyes. We had to bounce radio waves off the surface and back to a spacecraft to get these images of the planet. So now let's jet over to Mars, because we can do that in this software. It would take a very long time to jet from Venus to Mars in a spacecraft. But in the software, we can do it in about 15 seconds.
Give or take, if I don't get us lost flying across the solar system.
Okay.
I've had a little bit of practice, though, so hopefully we make it to our destination. I think so. That's looking a little bit better.
Okay. And here it comes. And it turns out there are many places on Mars where water can exist and where we find water today, including very thin clouds in the atmosphere. Some of those clouds, not all of them, but some of them are made from water. And something you can see that's bright at the top of Mars as it's coming into focus here is another place where water can hide on Mars, or where water is found. And those are polar caps. I mentioned on Earth that Antarctica is one of our polar caps, covered with water ice and snow. And that even the North Pole in the ocean, that there is ice that comes and goes with the seasons. Mars has polar caps too, at the North Pole and the South Pole. And those polar caps are made from water ice. So Mars is a planet that has water. And just like Earth, those polar caps shrink and grow with the seasons. So this is an animation that Jeremy is showing you right now of how those polar caps shrink and grow. When it's summer and warm at one pole, the polar cap shrinks. And then when it's winter, that polar cap grows. And they take turns shrinking and growing, because when it's summer in the north, it's winter in the south. Now, this ice on the polar caps that shrinks and grows is actually not water ice. It's the polar cap itself is water ice underneath, the part that never changes, but the part that shrinks and grows is carbon dioxide from the Martian atmosphere. Okay, so we've talked a little bit for Venus, Earth, and Mars about where we can find water. Earth has lots, Mars has some hints of water, and Venus has hardly any. So now let's talk about where water might go and how the planets might change. And let's stay at Mars right now. We might as well. We're here. We've already paid for the plane ticket. So let's go to a new place on Mars that we haven't shown you yet. And it's one of my favorite places on Mars. It's called Warrego Valles.
Take a little bit of time to orbit over to it. Now, Dave, as we're flying around, what are these different colored kind of regions or patches that we're looking at when we're seeing this. This is the surface of Mars, correct?
This is the surface of Mars, and some parts are, you know, orangish red or reddish orange, kind of bright red, and other parts are dark. And that's because Mars is a very dusty planet, and the dust gets blown around from place to place. And places where there are lots of dust are particularly red. Places where the dust has been blown off appear to be darker because you're looking down more at bedrock on the planet.
Great, thank you.
Sure.
And so, yeah, so now I think we're kind of centered up right above Warrego Valles here. And I'll start zooming us in so we can get a nice, you know, detailed look. We've had lots of, you know, orbiters and rovers even exploring Mars. So we have a lot of good, high quality, high resolution images that we can show you guys.
Okay. And as Jeremy brings this in, I'll tell you that this portion of Mars, pictures were first taken of it in the 1970s by a spacecraft called Viking that orbited Mars. And there were actually 2 Viking spacecraft sent in the 1970s. And so most of the images that you'll see here for Warrego Valles were taken by that spacecraft 50 years ago, almost 50 years ago. And as Jeremy zooms in, also in this region, it's high elevation near the top of the image and low elevation near the bottom. So think of a hill that goes from up to down over this image. Kind of like the up to down, you know, the mountains to the ocean that we showed you on Earth for that river system. And we're getting closer and closer to seeing it. And I'm not sure if you can see it quite yet.
We put on a little bit some postage stamps. Are we looking, Dave, right in kind of this bottom right-hand corner here? Is that where we're headed?
That's right. Keep going.
Keep rendering. Yep. Enhance.
Perfect.
Enhance.
Perfect, perfect, perfect. That's good right there. So now you can see all sorts of channels that are cut into the surface of Mars. And near the top of the image, there are lots of little channels. And they're thin and narrow, and they start to flow together as you move downhill towards the bottom of the image, and they make a larger and larger channel. This is a riverbed on Mars, and it's a river system, just like the one that we showed you on Earth. There's no liquid water running through that river right now, but it looks so much like riverbeds on Earth, not just the one I showed you, but many others, that scientists are really confident that this was once a flowing river on Mars. So we know that liquid water once flowed over the surface of Mars just from this one location. And the really cool thing is that the Martian atmosphere today would not make that possible. The amount of atmosphere Mars has today is too thin. There's not enough atmosphere for water to stay in the liquid form. If you put water as a liquid on the surface, it would immediately evaporate into the atmosphere. So the fact that this region exists at all tells you that the Martian atmosphere changed and planets change in general. There's another cool place on Mars where a rover is scooting around right now. It just arrived in February, a couple of months ago, the Perseverance rover. And it's in a place called Jezero Crater on Mars. And I think Jeremy's going to navigate there. Is that right, Jeremy?
That is right. We will zoom us on over there.
Okay, and I can tell you a little bit about why this place was picked as Jeremy goes there. There were many places on Mars that scientists wanted to send a rover, and almost all of them were places where we thought there were interesting features that might tell us whether Mars could have supported life in the past or Mars had liquid water in the past. And this crater on Mars, where the Perseverance rover is now, is one of those places. It's a lot more like the mouth of the river that we just saw on Earth, the place where the river meets the ocean. This is in a crater, and the crater has a break in the wall, and you can see a riverbed flowing through that break in the wall with no liquid water in it. And then you can see all the stuff that got transported down the river sitting in the floor of the crater. And that's what Jeremy's about to show us.
Yeah, we're gonna get a little flight in here now. You see we got our little landing site all picked for us. We'll go ahead and take that off, and then I'll keep on some of these high resolution images. And we'll see, maybe we can just land in the crater. How's that sound, Dave?
Perfect.
You can start to see right here. If we pause right here, you can start to see kind of the crater showing up. If I don't think you guys can see my mouth, or my mouse, excuse me. But we'll kind of go into the western edge of it, as Dave was saying.
Okay, and as Jeremy's doing that, we do have a question in the chat asking whether it's possible to date when water would have been flowing there. And yes, we can get an estimate of how long ago water was flowing there. It's challenging to do until we return rock samples from those locations. When we return rock samples, we can break open the rocks and see how long ago they formed. But until then, we have to use the context. So we look in the regions where we think the water was flowing. We see how many impact craters there are. And if there are lots of impact craters, then that region is old. And if there are very few impact craters, then that region is young. And so the places where water was flowing, we get ages that are around 3.5 billion years old. So a very long time ago that water was flowing. And here Jeremy is showing us the region now, Jezero Crater. There to the left of the image, you can kind of see a break in the crater wall where something flowed through. Yeah. And so water rushed through the crater wall and it formed this land inside the crater. And Jeremy can even kind of land us there and we can get a sense of what it would look like if you were the Perseverance rover.
Minus the sky, right, Dave? Would the sky be completely black if we were
It would
on
not.
the surface of Mars?
It would not. In fact, Mars is a very dusty atmosphere. So during the day, the sky would feel kind of reddish orangish, kind of like sunset on Earth. And then at evening, at sunset, it would switch to kind of purplish bluish. And this is what happens in a dusty atmosphere.
So here we are. We've got the atmosphere turned on. We've landed right where Perseverance rover is, and we can show you a little picture of Percy. If you guys are really interested in more of what Perseverance rover did, definitely go and check out this whole. We did a whole series on it, so very interesting. Lots of cool science there.
Cool.
Now let's see. We want to be. Go ahead, Dave.
What's up, Jeremy? What do you want to do next?
Oh,
here?
I was just going to say, we don't want to keep people all day, and we could talk for so long. So I think we've compared, Earth to Venus and to Mars. I think what we need to do really to wrap this up is talk about, a little bit of what you study. And, what's the point of all this? Why does it matter?
Sure, and I think we can do that without visiting more planets, but just by showing images. So let's do that for a few minutes.
All right.
So we've made the case that water exists on some planets today, and that water was maybe more abundant on Mars long ago, and that water was possible on Venus long ago, but isn't there today. So the question is, where can this water go? How do planets change? And so if I ask the question, where did the atmosphere go? There are only two answers that are possible, up and down. If there is water in the atmosphere or near the surface of a planet, then you could take that water down below the surface and it wouldn't be there anymore. We wouldn't be able to see it. But you could also take that water and remove it from the atmosphere out the top and have that water escape away to space. Both of these things have happened at all three of the planets that we've talked about today, Venus, Earth, and Mars. And what I spend my time thinking about is where the atmosphere went, and especially the up arrows. Let's talk first very quickly about the down arrows. What does water going down really mean? Well, one example is sort of here in this image, but Jeremy can bring up another one. Mars is red. You can even see that when you go outside at night and Mars is in the night sky. It has a reddish color. It's red because it rusted. Scientists use a fancy name for that. It's called oxidation. But oxidation, rust, they both take oxygen from an atmosphere and it interacts with iron-bearing minerals, so rocks that have iron in them, usually in the presence of liquid water, but not always. Mars is red, as you can see in the image on the right, kind of the color of rust, and we think that it oxidized. And so things that used to be in the atmosphere have been pulled out of the atmosphere and now go into making it the color it is today. In fact, when rovers dig down just about a centimeter, it's not red anymore on Mars. You can see that gray stuff that has been scooped out of the hole and dumped on the surface. The atmosphere didn't interact with that stuff, only the stuff right on the surface. Next, UPS. So let's look at a diagram of how atmosphere can change. You know, we've talked about atmosphere changing, about removing atmosphere in different ways. Here's a diagram that shows many, many, many different ways to change an atmosphere. And you can add atmosphere to a planet after it's already formed. If you see that picture of the volcano there on the left, volcanoes add atmosphere to Earth and other planets all the time. There are also all sorts of processes that remove atmosphere from a planet. They take an atmospheric particle and they give it enough energy that it flies away from the planet and enters space, goes to outer space. And there are many, many different processes that contribute to that. So we have to think about all of these processes when we're thinking about how atmospheres change. So we can think about how each of these processes would happen on all of the planets in the solar system. And the question is, how important has each process been for each of these planets? Okay, so let's move on, and we just have a few minutes left with you. So let's talk about two important things that could prevent an atmosphere from escaping: gravity and magnetic fields. Let's start with gravity. I think we all know what gravity is. When I jump up, it's what pulls me back down to the ground. When astronauts who are much cooler than me jump up, it's what pulls them back down to the ground. But if we show them again, I fall back down to the ground really quickly. Astronauts take a while to come back down to the ground. And that's because they're on an object, the moon, that doesn't have as much gravity as Earth. And that's because the moon is smaller than Earth. Little objects have less gravity. So if you could take an atmospheric particle and have it jump up on the moon, it would make it farther before it fell back down to the planet. And for really small objects like comets, then the gravity has a hard time holding on to the atmosphere at all. So the bigger a planet is, the more likely it is to use its gravity to hold on to its atmosphere. Small objects like this comet here, you can see the atmosphere escaping from the object. Almost all the particles can escape away because it's so small.
Yeah, some of you might be familiar with NEOWISE that came by last year. That's a good example of something.
Yeah, great. Okay, so let's go now to magnetic fields. And this is what my research center is thinking about. A lot of people understand gravity really well, but magnetic fields are something that people are still thinking about how they could help a planet keep an atmosphere. So I think we've all imagined what a bar magnet looks like with a North Pole and a South Pole. And all of us, no matter what age you are, have seen something like this, where the little iron filing particles organize themselves around a magnetic field. And that's because those iron filings have a charge, an electric charge. You could think of that sort of like static electricity. If you run a balloon across your hair, it becomes charged too. So anything that's charged changes how it is moving in the presence of a magnetic field. And this can be maybe important for atmospheric particles. Some of them can be charged too. And so magnetic fields can tell those atmospheric particles how to move. And when they do, we can get really, here's a sort of a cartoon image of what Earth's magnetic field might look like. It's similar to a bar magnet, just turned on its side. And that magnetic field for Earth is generated in the deep interior of the planet, in the churning core. So when that magnetic field influences how particles move, we can get really exciting things like aurora that make the sky glow near the North Pole or the South Pole. Those are particles in the atmosphere, but the magnetic field may also prevent particles from leaving the atmosphere altogether. And so if we think about Earth and Mars, one of those planets has a magnetic field, Earth, and one does not. And it may be that the magnetic field of Earth has helped it hold on to its atmosphere. And the magnetic field of Mars, which doesn't exist today, means that the Martian atmosphere is more ready, can escape to space more easily. So the idea is maybe magnetized planets hold on to their atmosphere and unmagnetized planets don't. And this is an idea that a research center that I lead is trying to test right now. We don't know the answer to that question, but we think that that might be the case. So I think it's time to wrap up, Jeremy. Do you think so?
Yeah, I think so.
Okay.
Real quickly, let's just, kind of summarize, we'll skip kind of over some of these, but Dave, if you just want to give us a summary of what this means kind of for the planets that we, the 4 planets that we're looking at right now. What does this mean? All this stuff that we talked about.
Here's some Jupiter, G, big G. It's a big planet, lots of gravity. That means it should hold on to its atmosphere. Big M has a big magnetic field. It should be even more able to hold on to its atmosphere. That means the amount of escape, E, for Jupiter should be tiny.
Right.
Jupiter should be able to hold on to its atmosphere really well. Earth, not as big as Jupiter, but big for a rocky planet. And it has a magnetic field. Both of those things smaller than Jupiter. So we expect Earth's atmosphere to be able to escape, at least some. And we think that that has happened over time, and we have evidence that that is true for Earth. Not more escape per size of the planet than Jupiter. Venus, same size as Earth, almost. So basically the same amount of gravity, but no magnetic field today. And that magnetic field might have been important for holding atmosphere there, holding the water on Venus. So escape might be more important for Venus than it is for Earth. And we have evidence that that's true too. Finally, Mars. It's little, it's only half the size of Earth, so gravity is small. It's like the astronauts on the moon, maybe not quite as bouncy, but almost. Okay, so it can't hold on to its atmosphere very well. It has no magnetic field, just like Venus. So that's no help in keeping an atmosphere. So escape on Mars might be very important and very big. So these are the ideas that we're testing, that we're trying to figure out about, and they're important, I think, because an atmosphere is important for having life at the surface of a planet. If we can figure out which kinds of planets can hold on to their atmosphere and which kinds of planets lose their atmosphere, then we can understand better where life on planets other than Earth might have formed. And so that's a really cool idea. As a scientist, working on a question like that is super, super exciting. So I'm happy to do it. And Jeremy, I was happy to watch you fly around the solar system and show lots of images really quickly while all I had to do was sit there and talk.
Yeah, I needed to catch my breath there a little bit, but I think we made it. I know we're at about 2:34 right now, so we're a little bit longer than our usual videos. But Dave, if you got some time and you'd like to, maybe field a couple of questions. I know you guys have been, I've been seeing lots of questions kind of pop up, and Ramey's been doing a good job of kind of feeding those to us. Let's see if we can just take a couple questions here. I don't think we've gotten to this one yet. But do planets around other stars have atmospheres, Dave?
Yes, they do. And it's really cool to be able to tell you the answer to that question, because we don't really have any pictures of planets around other planets. We have a very small number of images that just show planets as points of light, but most of our evidence for planets around other stars is very indirect. It comes from actually observing some other star and not being able to take a picture of the planet. So the fact that we know that they have atmospheres means scientists have come up with ways to figure out that they have atmospheres without ever taking a picture? And the answer is yes, they do. Some of those atmospheres have hydrogen. Some of those atmospheres have water in them. So we're even learning about the composition of those atmospheres. And we can even detect that some of those atmospheres are in the process of escaping away to space.
Excellent. We've got another question here asking what will happen to Earth's atmosphere in the future? And this is actually a great question because this kind of ties, this whole talk kind of together, I think.
Yeah, so let's talk about more the far future rather than the near future. That's a whole separate, it's a related topic of study about what life and humans on Earth are doing to our atmosphere right now, how we're changing the atmosphere right now. But let's think millions of years in advance, or tens of millions or 100 million years into the future. So at some point, Earth will use up the energy that's inside to drive volcanism. So Earth will no longer be adding atmosphere from inside the planet. So we'll just have the atmosphere that exists as it is. And at that point, maybe loss processes can start to take over in another couple billion years. At that point, then the Earth's atmospheric abundance will decline over time, but it won't be sudden. We won't all have to run for oxygen masks. It will take maybe several 100 million years to a couple of billion years for Earth's atmosphere to get to be as thin as that of Mars. But when the magnetic field turns off, when volcanism turns off, then escape will be maybe the most important process influencing the atmosphere.
Very, very good. Yeah, I mean, we might not be around for that. I know I will certainly not be around, but maybe some of future generations will have to figure out, how to deal with that problem. We've got another good question from MP Donahue, and it has to do with seasons on Mars. So MP Donahue says that does Mars have a similar tilt of its axis to Earth? Do other planets, and why?
This is a great question. So, and it's a question that I would give to college students on an exam, worded exactly in this way. So Mars does have a similar tilt of its axis to Earth. Earth's axis is tilted 23.5 degrees with respect to the plane in which it is orbiting. So in parts of the year, the North Pole is oriented towards the sun, and in other parts of the year, the North Pole is pointed away from the sun. And it's very stable over time. Earth doesn't flop around very much because we have a large moon that stabilizes our tilt. The Martian axis is currently tilted 25 degrees with respect to its orbital plane. Earth is 23.5, Mars is 25. See the difference? That difference is huge right there. It's hardly any difference. However, what is different between Earth and Mars there is that that tilt changes by large amounts over time, over millions of years. That 25-degree tilt varies between maybe 15 degrees and almost 60 degrees. So Mars is doing this over long time scales, and sometimes like this and back and forth all over the place. And it's so chaotic like that because it does not have a large moon to stabilize its tilt. So this big change in tilt on Mars might mean that the polar caps sometimes are very, very large. And at other times in Martian history, it might mean that they're much smaller than they are today. So what we observe today on Mars doesn't have to be how the polar caps look all the time.
Okay. Yeah, great question. Great answer. I love your, when you act out these answers. It always makes it a little bit easier for us to understand these types of concepts, even virtually. So thank you for that. And I think with that, if there's any other burning questions, go ahead and type them in that chat. Feel free to always comment on these videos too, because we'll go back and answer anybody's questions after the fact. But we want to be respectful of everybody's time today. Thank you again for joining us on this very special Dome to Home episode. It's been a couple months in the making. We were glad we were finally able to go ahead and get it out to you guys. I just got a reminder from Rami behind the scenes that you can also submit those questions using the submission form. Those links are down below. We also have links to our series, to our website. If you guys have any questions for us, just reach out, email us. We love to hear from you guys, and we do all this for you. I want to say for next week or this upcoming week, we have another Dome to Home show on Wednesday, but we're back to our normal scheduling of studying the Earth. This is, Earth Month is what I'm calling it, or with Earth Day coming up on the 22nd, which is Thursday. I just realized that's coming up very quickly. We'll have a special Dome to Home episode on Wednesday. Once again, Dave, I just want to say thank you very much. We really appreciate everything, and we know you're a very busy man. Thanks for taking the time to spend a little bit of time on Dome to Home with us and teaching us about Mars, water, magnetic fields, Earth, everything else.
Thanks for having me, and I'm always happy to chat about things like this.
All right. Until next time, same channel, like, share, subscribe. We'll see you next time.